Hi, everybody. Welcome to Kingspan Digital Academy today. We're just waiting just a minute for people to come in as we have a fair few numbers on today, and we just wanted to get everybody loaded in on that front. So just hang one moment and we'll start and bang on 12:30. Okay. Thank you for waiting for just a few people more to load in there. I'm Victoria Alvin. I'm the General Manager of Building Technology and Technical Services with Kingspan Insulation New Zealand. It's my great pleasure today to welcome you to our Kingspan Digital Academy. Our topic today is warm roof design, focusing on Kingspan insulation. So as you know, warm roofs are becoming more and more popular for residential and commercial buildings. So today we're going to be looking at, well, how do I know when I'm supposed to do a cold roof design and when I'm supposed to do a warm roof design? What's going to be successful for me? What are the different types of warm roof design I could consider? Different membrane types, different insulant types. What is Kingspan Therma PIR all about? Is it the same as every other PIR? Spoiler alert, no, it's not. And how do I install it? How could I create fall in my roof when it's below minimum pitch? And I don't want to repitch my roof, so we'll talk about tapered PIR. And finally, what sort of technical support can we give you to ensure your project's a success? So if we start today, those that joined us recently, we had a great presentation on roof condensation, focusing on cold roof design. Now that webinar will be shared with you out from today's webinar as well. So you'll get a twofer, if you like, today's recording and that roof condensation one. But in that webinar, we spoke quite clearly about the condensation issues that we can see in cold roof design and some of the limitations in cold roof design when the factors that are necessary for a successful cold roof design aren't met. Now, often one of the major driver for development of sites is maximizing lot yield. And this can be buildings that are not optimized for solar. So it can have a very negative effect on the performance of a cold roof design. Now this, the solar element, was what we saw in an article we referenced in that roof condensation webinar, Build 180, a school lesson, a Brands article saying, why did this cold roof design not work? Why wasn't it successful? Well, as you see in the image on the right, the solar lines aren't hitting our affected roof for 5 months of the year. So a cold roof design needs sun to warm it up. It gets very effective by the eternal moisture load coming through the building. So this is a school environment, so there was no internal ceiling control for internal moisture migrating into that roof space. And you think of a lot of school children coming in and so on, might be wet from the playground. So the roof's getting overwhelmed with moisture. The sun's not hitting it to dry out, and the roof's just not getting warm enough. The ambient temperature is about 15 degrees because this is in Dunedin. So the roof is literally raining within the structure. And that's one of the designs that would have been better designed in a warm roof design. So that's what we're talking about today. What are the factors that are driving warm roof design? You may consider a warm roof design if the climate is too cold or too humid. Does the roof actually get some sun on it? Now, this image that I have here on screen is a classic example where you can see the frost has melted off where the sun is hit, but the roof that's still in the shade is significantly cold and the frost still remains. So when we're designing for a modern site, maybe 500 square meters or less, we might see that the solar lines never hit this roof. The orientation of that roof, because it needed to fit to the site, is not ideal for warming up and creating that drying effect that we need in a cold roof design to take the moisture out. If you remember, a cold roof design is where the structure is outside of the insulated envelope, and they can get moisture within them that needs to be dried out by returning it back into a gaseous state so the ventilation pathway can take it out. If the roof pitch is very low, again, improving our height boundaries on a very compact site, then we might not see the ventilation that we need as well within that roof. And the wind speed can be impacted because we have a lot of houses built together. The wind speed will affect the ability of a roof to ventilate. So lower wind speed, less ventilation that's driving that roof. And then the condensation probability starts to rise. We also saw in our roof condensation presentation how much the internal moisture load affects the roof design. So The factors that might drive a warm roof design are, do we have an internal moisture load that is high? Do we need to contain it? What would be the type of roof design that would work best there? And of course, operational energy for a building is always going to drive a design that's easier to maintain and keep our building warm. So what is a warm roof design? Well, a warm roof design removes many of the compromises that exist with traditional cold roof construction. The roof system no longer has to deal with moisture loads from the dwelling inside because there's a vapor control layer under the insulation. The insulation's over the top of the structure, so the structure is kept warm, which means that it's dry. It no longer has that condensation, wetting and drying cycle that can cause the structure perhaps to degrade before its time, or the cladding materials. The ceiling space is warm because it's under the structure, which means if you have services in the ceiling space, they may not need as much energy to run as they do when they're sitting in a cold roof design. There are no specific New Zealand standards for warm roofs, but they must meet B1 structure, B2 durability, C1 fire, E2 external moisture, and H1 energy efficiency. So a warm roof design is typically a proprietary system, something that has been carefully designed for all the components for compatibility and for performance. We're going to stress that a little bit later and talk to you about why it's so important to follow a proprietary design. So what does happen in a cold roof design and how is that impacting my building performance? What actually is the scientific difference? Well, here in the cold roof design, that blue line represents the metal roof temperature that fluctuates throughout the day and night. When we were talking about this in our roof condensation webinar, we talked about the outdoor temperature and the effect on a metal roof. You can see there that the blue line at the bottom is below the green line being the outdoors, the blue line's the roofing material. So you can see here that the roof is getting much hotter than the ambient air during the day and colder at night due to night sky radiation where the heat loses its temperature. Now, of course, at a lower pitch, you get more night sky radiation, so you get an even colder roof. So that can have quite an effect. Here, we now have the house temperature in orange. So you can see in a cold roof design where the insulation is below the structure, you can see the image on the right there, the insulation is a standard truss roof design at ceiling level. The house is going up as the roof heats, coming down, but staying much hotter and can be overheating. Now, on a darker color roof, that roof might reach 90 to 100 degrees Celsius, and that will contribute to the house overheating and mean that we might need higher cooling costs. Brands here modeled a warm roof design. Now, this is in the ventilation testing facility that they have in Wellington, where if you recall from our last presentation, they were modeling the air changes within a ventilated roof. And so this is an example when they made a warm roof, how it modeled. In this diagram, you can quite clearly see that the warm roof, sorry, I had a Teams call coming in right at that moment. I had to can it, so it distracted me. You can see that the temperature fluctuations are evened out throughout the year for both the structure and the internal environment. So there can be a reduction in heating and cooling costs, which is often cited as one of the benefits of a warm roof. So there are many different types of warm roof design. A built-up roof can be ideal for moderating construction costs and retrofitting to an existing design. It allows customization for both acoustic control with the addition of acoustic boards, for both keeping rain drum out, for trafficability, the amount of people that are walking on that roof, and even snow loads in different designs. The external cladding in a built-up warm roof can either be profiled metal, which has a minimum pitch of 3 degrees, or it could be a membrane, which can go down at times to 1 degrees. We know E2AS1 will say that a membrane is a minimum pitch of 2 degrees, but many membrane suppliers have a certification that will take their membrane down to 1 degrees. It just needs to drain for roof drainage on that front. A membrane roof, again, is often used where we might have, in this example, as you see in the middle, an apartment building. Higher wind zones are meaning that a membrane roof is more ideal. They're easy to install and put together as a warm roof. An insulated panel, as you know, we do have Kingspan insulated panels as part of our portfolio, is also a one-stop shop for warm roof design, where the lining, insulation, and enclosure are all one. Now, of course, traditionally, panels have been limited to a particular length that could be imported, but now with New Zealand manufacture, we can see lengths of up to 24 metres, which makes designing with an insulated panel a little bit more easy than it has been in part. Each of these systems has different advantages and disadvantages to them, and they are commonly proprietary systems or have proprietary details to them. So the system provider will be able to talk to you about what is your project and what you particularly need in terms of a system. For waterproofing membranes, cold liquid is a coating that cures to form a rubber-like waterproof membrane. It can go over many substrates such as concrete. It's considered to have less fire risk. It's fast and easy to apply. It can be applied over existing roofs. But Kingspan does not support the use of liquid membranes direct to PIRs. It's not considered robust enough. We do support the use of both single ply and bitumen torch-on membranes. So a single ply is one of the most popular flat roofing materials for both commercial and for residential. It can be used with green roofs or exposed roofs. They have systems for adhering, for Velcro or mechanically fastening to the PIR or insulation substrate. Normally PIR in these types of systems because of its compression and its ability to be walked upon. A torch-on creates a multi-layer membrane for roofing. The roll width is generally more narrow at 1 metre, so there are many joins, but the benefit is considered to be much more robust. The torch-on system commonly has a self-adhered or mechanically fastened base sheet, and then the torch-on is laid over that. Again, the membrane supplier will be able to advise specifically for your project requirements for durability, performance, and so on. A more traditional construction technique for warm roof is with a concrete or plywood substrate. Now, the concrete can be created with the fall that creates a drainage, as can the plywood, or they can be flat and the drainage can be added with tapered PIR, polyisocyanurate rigid insulation boards that have the fall already built into them. We're going to talk a little bit more about that shortly. So as with the metal tray substrate, the use of a vapor control layer under the insulation above the concrete or the plywood is important to make sure that the internal moisture does not migrate into the warm roof system. These systems can be adhered or they can be mechanically fixed according to the specifications provided by the system provider, but they're normally very quick to install and a great way of weather tightening and insulating a structure. Kingspan Insulation has a white paper that's going to be released soon, and it's focused on the thermal comfort that can be achieved with the addition of R3.3 insulation to a roof. We look forward to sharing the white paper with you when it releases, because remedial or retrofit for existing buildings is often a great time to add insulation. And homeowners and business owners like to see what sort of benefit they can be expected to see out of adding insulation. So typically, a waterproof membrane is going to be replaced anywhere between 10 and 30 years, depending on the environment and the performance. At that stage, it might have been that the insulation requirements in New Zealand were not as they are now, highly likely, and there's less insulation than the occupants feel is ideal for their thermal comfort. We've become much more used to being warm in our homes, and we no longer like to be cold. So when replacing the waterproof membrane, it presents an opportunity to insulate both the roof deck at the same time without the need to vacate the occupants or pull that system apart. It provides indoor comfort, it reduces heating or cooling, and it can deliver lower carbon emission buildings. Very simple to do without disturbing occupants on that front. A warm roof design requires a continuous substrate. A metal tray substrate is very popular as the building is enclosed as soon as the carrier tray is laid, and the carrier tray can span further than plywood can. A vapor barrier again is installed between the substrate and the insulation, and that may either just be tape on the joints of the metal tray or could be a full vapor barrier that's laid over the metal tray. It can even be used as an overlay system on an older roof, reducing demolition costs and containing elements such as asbestos, as you see in the top left image. There are many different styles of this type of roof, some with a profiled metal on the top, which would be direct fixed the whole way through the system, or some that have a membrane system on the top as well, which might be adhered or glued together as part of a system. Each system again has its own advantages, and each proprietary partner will be able to explain what is most suitable for their design. Retrofitting warm roof to a metal tray was a topic that we spoke about at the RANS conference recently in June. This type of profile, Diamond Deck 400, for example, was very common in the 1980s, early 1990s, and at that time was often installed at a low pitch, perhaps 1 or 2 degrees. So now it might be creating fall or have some issues with how the roof is performing. Again, at that stage, there wasn't a significant amount of insulation within the roof structure. So as people look to re-roof and re-weather tight their building, adding insulation can be a fantastic way to get more thermal comfort out of their home. It's very simple. The PIR is added within the trough of the tray of the profile, a vapor control layer, and then built up with more PIR and the system, the weatherproofing system of choice, either profiled metal, which is fixed through the elements into the structure, or a membrane system, either mechanically fixed or adhered. As we saw before with retrofitting over a membrane roof, the same advantages exist. There are no demolition costs of the original roof. Assuming that the original roof is tests fine for structure and will hold the new roof weight, PIR being a very light material, it's quite easy to do, that roof can simply be overlaid. No disruption to occupants or business. One of the stories I heard recently about was a light commercial build with several shops below it that needed to be re-roofed for weather tightness. By creating a retrofit system over that metal roof, there was no disruption to business cost, and the metal roof actually worked out to be less expensive than replacing the roof and the disruption to business cost. So having a look at how that will price up in terms of retrofitting can be quite an advantage. Of course, it adds insulation and improves the thermal comfort, which might improve the performance of that room below in terms of heating and cooling. And if there's not enough fall, we can just add tapered insulation to this roof and create the fall in the insulation, perhaps going from the 1 degree pitch to maybe 3 degree pitches. Also known as garden roofs or living roofs, these proprietary systems vary on planting methodology and design requirements. There are very strict design requirements for the vegetation, the type and the root structure, and the weight of the system. It needs to be considered early in design because the structure needs to accommodate that weight of both wet soil, dry soil, plants as they're grown, and so on. But these roofs are very popular to reduce stormwater runoff, water purification, protection from climate extremes. They may even be part of a covenant on a site where something, a building needs to blend into the landscape. Again, proprietary systems, and they do need to be carefully designed. This is a design element that would be brought in at a concept stage. Finally, a concrete deck is normally considered an area that can be accessed by doors. That might be the balcony of a living area, or could be the roof of a shopping centre where the shoppers are below staying warm and we're dining above in open air restaurants. In this instance, the surface finish can be a variety of options, such as stone ballast, membrane pavers, modular decking systems, or even gardens. In some designs, the deck may not have fall, and the addition of screed to create the fall is not possible due to the weight of the system. We would commonly see this on a balcony, for example. So instead of screeding to create the fall will be created by a tapered insulation. But in other systems, the fall might be flat and it could be designed as an inverted roof. Again, it's a proprietary system. So what are the different insulants? We've been talking about PIR so far, but there are different types of insulants that sit within warm roof designs. And there are many factors as to why a proprietary system would have looked at this insulant over another insulant. Some quick guidance. If your roof needs compressive strength so it can be walked on, fire performance, if it needs a thin thickness, high R value, PIR boards, polyisocyanated boards, are very hard to go past. They are thermoset closed cell insulation and are the leading product in warm roof design. They can be adhered or mechanically fixed to the substrate, and different faces on the PIR board can mean that different membranes or weather tightening systems can be incorporated in. For thicker roof structures where height is not as important, a fibrous insulation can be used, and some of those products are also non-combustible. These systems often have mechanical fastening systems, so they're not adhered. And of course, bio-based materials such as wood fiber can also be incorporated into a warm roof design, giving us great upfront carbon storage in the system. So choosing the insulation depends on many different types of factors. Again, we need to go back to the proprietary system partner and look at the testing and performance they have with different insulant materials. But if you look here, what I have pulled together is an R6.6 material value. We know with the new H1 changes that now our roofs will be in a calculation method where we might be balancing the R value of the roof against an R value of the wall and trading off the R values between these elements. By standardizing at R6.6, I'm just providing a comparison between these materials. On the left-hand side, I have different types of PIR with gas-tight aluminium faces and a glass tissue-faced PIR. I'm going to talk more about those in a moment. You can see that a gas-tight aluminium facer is the best thermal efficiency per thickness, whereas by the time I look at a bio-based material such as wood fiber on the right-hand side, I'm a lot thicker to reach the same level of performance. But the carbon for wood fiber-based material is far better for upfront carbon storage. In the middle sections, we have rock wool, EPS, and glass face BIB, so glass insulation. Between rock wool and BIB, we might be considering non-combustible materials, but then we're looking at the height that we have, which might affect our roof height bounds, and perhaps the weight of the system between them. An EPS in the middle needs to be considered in terms of fire and moisture balance, where an EPS or an XPS, an extruded polystyrene, must be protected from fire and are unsuitable where hot bitumen, asphalt, or solvent-borne adhesives are used, unless they're specially formulated for those products. An EPS would be considered a thermoplastic material, and thermoplastic materials in a fire will simply melt away from the fire, whereas a PIR is a thermoset material, which means that it will char in the presence of fire. So they have very different performance in terms of fire. Kingspan is one of the world leaders for manufacture of PIR rigid insulation and has been so since 1965. We have PIR products to meet all system needs and support our products with environmental reporting, such as environmental product declarations, and a commitment to manufacturing that is free of CFC and HCFC gas blowing agents. That means that we have zero ozone depletion material. The advantages of PIR include it's an excellent insulator, it's a closed cell structure with a high resistance to moisture absorption, self-extinguishing in a fire, and do not melt. As I said, they simply char in a fire performance. Excellent durability, and they can be faced with different materials to provide different compatibilities with different membrane types. Any material produced in a Kingspan factory globally will have full material and production traceability through Kingspan's ISO quality and control programs. So let's have a chat about those faces that I was talking about. This is actually very important in terms of the reporting of a PIR and how they work. This is called a glass tissue facer. You can see on the front of it, it has a perforated and it's got what's a glass tissue. Now, I've used TR27, which is our key glass tissue product, but we do have other products with different names. I'm comparing it to a gas-tight aluminium facer. This has got no perforations in it, and the gas-tight aluminium means that the thermal performance of the product is different. The key difference we'll talk about first is what you can adhere to them or how they go in a system. A glass tissue-based product is compatible with most bitumen and asphalt-based waterproofing systems. Single-ply, non-bituminous membranes are also used that are fully bonded with solvent-based adhesive systems. So I can adhere my board into my warm roof system, or I can mechanically fix it. But a gas-tight aluminium facer, this product, TR26, for example, TR26 is not suitable for adhesive systems and is mechanical fix only. Both products have got excellent compression. Why does that matter? That means that you can walk on these products without damaging the PIR. A PIR with less compression will be damaged by foot trafficability, which breaks the seal between the facer and the PIR, which allows the system to uplift and wind. And of course, they're both tested to Australia Standard 2122 for fire performance, thermoset rigid insulation. What else is different about a glass tissue and an aluminium face board? It comes down to how they perform in terms of thermal performance. So we often talk about the lambdas, the thermal conductivity of a PIR board. And when we're talking about the lambda, the lower the lambda, the better the product performs. The higher the R value, the more thermal resistance the product has. So my gas-tight So my glass tissue faced board at 100 mils has got an R4. The gas type one's got an R4.5. Gosh, well, why is that different? It's the way that the gas tight aluminium facer contains the gas within the board and provides the same lambda across all thicknesses. A glass tissue board will have a different lambda for different thicknesses. Now, that's the key thing that I want you to remember there, but I'm also going to talk about the testing of this product. In New Zealand, we have to report our insulation to Australia New Zealand Standard 4859/1/2018 at 15 degrees. At 15 degrees, it means that that insulation has been tested for New Zealand temperatures, and these boards will perform differently at different temperatures. So at 15 degrees, that's the R value that we're looking at. If the data sheet says 23 degrees, I'm now looking at how this board will perform in Australia. It doesn't mean it's going to perform the same in the New Zealand, and the R value will not be the same in New Zealand. If it says 10 degrees on my data sheet, that is not the temperature at which it will work in New Zealand. That is the temperature at which that board will perform in the UK. So I need to see 15 degrees, and I need to see an aged value. PIR, when it comes first off the line, has a really low lambda. It might be 0.020. That's called an unaged lambda. It needs to go through the aging process as outlined in that standard, where at 175 days at 70 degrees, we artificially simulate the aged value at 25 years. And then we will do a statistical analysis and report the samples for the whole range of thicknesses within that board style. So when you look at a data sheet or a selection of products, you're looking to see, have I got different lambdas for a glass tissue faced product? Does it make sense that my gas tight aluminium facer is sitting around 0.022? Is the client or is the manufacturer reporting a declared product value at 15 degrees in accordance with 4859? You might see sometimes online a product that will have glass tissue, unfaced PIR, perforated aluminium, and gas tight aluminium, and they'll report the same lambda and thermal performance for all of them. I could challenge that supplier and say that is not an accurate representation of their product and market. So not all PIRs are the same. As I've said, PIR is not a commodity product. It can be very different in terms of both fire performance, compression, and R value. A proprietary system as a warm roof system is often a membrane or built-up system that has all the components tested for performance. Adhesive compatibility, membrane compatibility, wind uplift for both adhesive or mechanical fastenings, H1 compliance, and fire performance. To achieve the warranty and performance, it's normally necessary to purchase all components through the system provider. If you purchase the components outside of the system provider chain, you may find that the warranty is no longer applied to that system by the system provider. Changing other components such as PIR, adhesives, or other elements could also reduce the system performance. Now, Kingspan is very proud to be part of systems with Roof Logic, Viking Roof Spec, and Diamond Advanced Roofing Systems. The compliance pathway is a mix of PS1s, brands, or code mark with these systems, and they will provide a pathway for your project that you can trust and rely on. Installing PIR is very simple to do. It's a very quick and fast process, and you'll see that the boards are offset to reduce any potential for thermal bridging and so on. We do not line up the joins on the boards. And as mentioned, we have an adhered or mechanically fastened system. Now, whichever method is used, the proprietary system partner will provide testing for compatibility and performance. Wind load calculations will have been determined in the fastener requirements in the corner, perimeter, and roof areas according to the pressures that face that roof. The adhesive will be tested for compatibility and performance, and it can be more expensive than mechanical fasteners. However, mechanical fasteners can have an aesthetic impact that some clients don't like. That is part of the discussion when designing a warm roof system as to what the expectation is of a client of their roof and how they would visually like it to look. We can also create the fall, the drainage in a system using tapered PIR. So we can start with simply either a system that does not have sufficient fall existing or a flat concrete, plywood or metal tray system and add the fall with a tapered PIR. It means that we've got very accurate fall. A screed system, which is the alternative, can be variable in terms of the accuracy of fall, but using a tapered insulation means that the fall is particular. And the diagram that you see on the top right, that's a 1 degree example. The first tapered board starts at 30 and rises 20 mils to 50. The next one goes 50 to 70, and then 70 to 90, and then 90 to 110, and then a packer board is put in and the system starts again. Kingspan will design those tapered systems for you using the fall that is required as part of the proprietary system. So we have a lot of different proprietary system partners in New Zealand. They hold stock in different fall products, both in 2 degrees, 1 degree, 1.19 degree, and it depends on what the system is calling for as to which tapered fall is required. Sometimes when we see plans, we'll get quite a variety of falls, 1.36 degrees, 1.89 degrees. So I need to make sure that I've clearly explained that the tapered board comes in very set degree formats. And even in a screed, it is almost impossible to design those very particular pitches. Very happy to work with architects on that to get a sustainable tapered design. The other reason that tapered systems are used is to reduce the weight out of a building. If the building needs to be re-insulated and re-weather tighted, adding screed to create the fall can create issues with regard to the structure of the building. But designing the weight out of the building at the moment can really reduce the cost of a building, and adding tapered insulation creates that fall on a flat structure. It also improves the construction timetable. As we mentioned in our previous webinar, concrete takes about 25 mils, takes a month to dry. So a screed layer over an existing roof or over a flat concrete roof can take a significant amount of time to dry well before the next stages of building can proceed. We can also create your tapered designs for you. The team that we run here at Kingspan is capable of taking a design and building it into a full tapered program for your roof in conjunction with one of our proprietary system partners. We'll simply take the design details, discuss with you what might be required and what your overall ambitions are, and work with that proprietary roofing partner to bring that design to life so it can be priced and then installed through the registered installer network. Kingspan Technical at kingspaninsulation.co.nz is your first port of call to send designs or ask one of our specification team to come and talk to you about your project that may require taper insulation. So today we've learned that a warm roof has insulation above the deck, keeping the structure warm. It can keep the structure drier, giving more durability to the roof as well. It significantly reduces the risk of moisture accumulation and enhances the thermal performance of the roof. It can be ideal where the circumstances are not suitable for cold roof design. It provides a functional and highly efficient roof design. But a warm roof system does require careful design, and it does require performance modeling. Always use a proprietary system with a pathway for compliance and a system warranty. Would you like to learn more about other ways that you can mitigate thermal bridging in your design? Join us for a webinar on continuous insulation for both roof systems, perhaps more built-up systems or retrofit systems, such as retrofitting a skillion roof in a Lockwood design. Perhaps you'd like to talk about timber and steel framing and concrete walls and how you can insulate those walls to mitigate thermal bridging, especially with the new changes in H1 that might see a mandatory 38% for timber for bridging and timber framing. We are going to talk about the money, balance up some systems in terms of what do they cost and what their thicknesses are. And we're going to talk about the different drivers that influence different types of continuous insulation design. So please join us on the 11th of November for that topic. Finally today, technical at kingspaninsulation.co.nz. If you've got any questions, we're going to take them there after this presentation. We'll take questions in a moment. And at the back of this, again, is some bedtime reading for you, some of the references that are used as part of this presentation. Today, I'll leave this on this screen, and Marie Maxwell, who's our technical lead here at Kingspan Insulation, is running my chat for me today. We'll take questions that we might have. Marie.
First question, what are the weight limitations when adding a tapered insulation system to a DD400 roof?
That would depend on what the structure is underneath that DD400 and the span and so on. So any retrofit system for a roof, we need to be able to look at the structure and understand what is the structure of that roof, and then looking at the elements that are going on top. To give you an example, I think a tapered insulation generally sits about 32, 35 kilos per meter cubed in terms of weight, whereas if you were looking to add screed, maybe not over a DD400, a screed sits around 2 tons sometimes per meter cubed. So the weight consideration is huge for tapered and one of the distinct advantages.
Um, can height safety anchors be used over PIR warm roof?
Absolutely, but I would think that they would need to be designed through to the structure for the height safety system. Again, that would be a proprietary system detail. It would depend exactly on what type of system is being installed, but that conversation would be had with the proprietary system partner and the chosen height safety partner to ensure securement and performance of their system. But yes, I would think that would be very possible.
Is a staggered insulation board layout or a double layer required for systems like Roof Logic?
I would think RoofLogic would be normally following a staggered board layout system, but it might depend exactly what they are doing in that system. But it's a general standard for PIR or any rigid insulation material that the boards are offset in a staggered system to prevent thermal lines going through. RoofLogic has other insulants within their portfolio as well. So they might talk to you about what your limitations are on design and what you need to achieve, and then direct you to the appropriate insulant and layout for your project.
And um, our good friend Sylvan wants to know if PIR board is suitable for use in a warm roof application.
Do you know that that's such an interesting question, Sylvan, and thank you. We did have a system design recently that called for a gentle curve on the PIR board, and you could cut and create a curve in the PIR, but as you can see, that's quite a rigid material. So I think that would be an engineered solution where both myself, the proprietary system partner, the installer, would look at the curve and what's required and work out how we were going to create that system as a functional system and ensure that the board can be adhered and not spring back and then the membrane can go over. That would be a a project where we would desperately want to be involved with from the beginning to ensure that we've designed the system well. So that's a specialist design project.
And lastly, what are some of the recycling abilities for PIR? Is there any solutions to these for the future?
I do love this question. So, Kingspan, in terms of our environmental product declarations, always reports to end of life and recycling. Now, in the UK, that's an easy story because we would send our PIR to a burn plant and it would be turned back into energy that's supplied back to the district and so on. In New Zealand, we don't have those plants currently in place for PIR. So we can't report on the recycling methodology that's used overseas and say that's how we perform in New Zealand. However, there is discussion underway at the moment that is still being finalised for the PIR to go as a fuel source into concrete manufacture. And I can't tell you how excited I am to see that project actually getting legs and almost at fruition stage where we can see the material that we're taking off roofs or even the waste offcuts being used for another purpose, creating a more circular end for the material. So when we have that story fully finalised, you can be sure you'll hear that shouted from the top of the mountain because we'll be so proud. Kingspan does have a very proactive and I would almost say aggressive planet passionate program to improve our built environment. We have some very key guidelines as to how we improve the recycling of all our products, not only our PIR, and you've probably heard about our Save Board program, where all our construction waste for underlays, sorry, all our manufacturing waste for underlays and construction waste is recycled back into Save Board materials and used, the first circular solution for underlays within the New Zealand built environment. We would very much like to see the same conversation happening for PIR, especially as we have our PIR plant in Australia coming online, and we hope to be producing PIR for supply in New Zealand before too long as well, rather than using our European plants. So our EPD for Australia, of course, all our EPDs for Australia include the transportation to New Zealand. So for an Australian EPD, it has transportation for New Zealand. For a European EPD, that transportation isn't factored. Any other questions there, Marie?
Yes, there's some additional ones. May lightweight insulating concrete like pumice or perlite be used as a structural element over steel decking to form a composite roof, or does New Zealand does not allow it?
I think that's outside of my realm. If we're talking about, did I understand that question? Is that talking about the concrete that's used in a composite steel decking like Comfort
Yeah,
or High Bond?
yep, yep.
Um, sorry, that's outside of my guidance for this presentation. However, many of the composite steel decking manufacturers will talk to you about their types of concrete. I'll have to, maybe we can just take note of that one and we'll direct them to some of the technical managers we know over in composite steel decking.
Good. And what is suitable foam to fill gaps in PIR?
Uh, As with our cool therm product, we would always say a non-solvent polyurethane expanding foam. We have a variety that people have worked with in the past, but commonly is part of a proprietary system that will still be tested as part of their system to ensure that they have compatibility. There are some very detailed requirements about chemical interaction that are listed on our data sheets for PIR as to what chemicals cannot be used, but as general, a non-solvent polyurethane expanding foam would be ideal to fill the gaps that you might see between insulation materials.
That's it.
That's us. All right, well, thank you very much. I'm sorry I ran over a little bit with the questions there. Join us on the 11th. We hope to see you again there. Thanks for joining us today. This will come out as a recording as well as the roof condensation one. Have a great day and thank you so much for your time.